Application of equal area criteria. Under the application of equal area criteria, first we'll see what happens when there is a sustained fault. That is, which is tested for generator which is connected to infinite bus through a parallel feeder. I am taking this as one of the application of equal area criteria. Based on the equal area criteria, whether the system is stable or not, we have to check for this particular the case. The system is shown here, that is the generator is connected to infinite bus through the parallel feeder here. There are two feeders, they are connected in parallel. Now there is a fault is occurring, that is a sustained fault is occurring at midpoint of one of the feeder. Then subsequently when there is a fault occurs, this particular feeder is taken off from the service, because of faulty the feeder can be taken out of the service. In that case, whether the system is stable or not, that you have to test using the equal area criteria. That is why first, without fault, then when the system is a healthy condition, that is there is no fault on the system, in that case these two we have to find out what is the power angle characteristics of the machine, that is the output of the generator which is connected to the infinite bus. Here the two reactances they are come in parallel, that is in series with the reactance of the generator. Then here the power angle characteristics, that what I am showing here is this is the power angle curve A, that is before the fault occurs, these two reactances they are come in parallel in series with this reactance of the generator. Then the power output of the generator P is given by EV by X into sin delta. Therefore, this the curve what I am getting for the output of the generator which is connected to infinite bus. Subsequently, when there is a fault is occurring, this particular faulty line is taken out of the service. In that case, ultimately the reactance of the system is increasing from generator to infinite bus. Because this line is taken off, ultimately the reactance from the generator to infinite bus is increasing. Thereby, your power angle characteristics is shifted to a new value. That is what I am showing here. The curve B, that is post fault, where the fault is cleared, so that this faulty line is taken out of the service. Then this is the curve what we are getting here when the fault is cleared. Before the fault occurs, the generator is operating at point M. Subsequently, when there is a fault is occurring and the fault is cleared immediately, so that this line is taken out of the service. Therefore, the operating point is shifting from M to here N. That is, previously it is operating at M, then it is subsequently it is shifting to N, because the output of the generator is reducing, because the reactance from generator to infinite bus is increased. Therefore, the operating point is shifting here, where PS is the mechanical input to the generator, which is a constant. Now, at point N here, there is a situation arises that the electrical output, that is the electrical output which is less than the mechanical input M here, that is PS. At the point N, the PE is less than PS, so that the generator has to, that is there is an acceleration, the acceleration. Because of this, what happens, the angle delta is goes on increasing in the case of generator. That is what we have discussed so far is for the motor. In the case of the motor, when there is the excess power, that is output is less than the input, in that case, in the case of the motor, there is an acceleration, speed is increasing, whereas the angle delta is decreasing. But that is exactly opposite case in the case of the generator, that you have to keep in mind. That is, in the case of the generator, what happens, the output is the less, than the input. Therefore, there is acceleration. Here, instead of angle delta decreases, here it is increases because it is generator. Therefore, from n onwards, that is angle delta is goes on moving on this red curve. That is, it is moving from n to, it is O. It is n to O. That is, at n, at m, it is operating with a synchronous speed. Here also, when it is shifting to the n, still the speed is synchronous speed. When it is shifting on n, there is an acceleration. The speed is goes on increasing from n to O. At O, what we are getting here is the electrical output and the mechanical input both are equal. However, because of the inertia, delta is goes on increasing. Delta is goes on increasing. But the speed is increased from here synchronous speed to more than the synchronous speed. And the O onwards, the angle delta is goes on increasing because of the inertia. But however, the speed is goes on decreasing because above O here, that is electrical output is more than mechanical input. Above O, then your electrical output is greater than the mechanical input. Therefore, there is a deceleration. Therefore, what happens here? Here the speed is goes on decreasing. Ultimately, when it reaches the point P here, when it is reaches the point P here, then the speed is becomes synchronous speed. That is, here it is speed is synchronous speed. At O more than the synchronous speed. From O to P, the speed is goes on decreasing. At P it is a synchronous speed. Then when it is reaching a synchronous speed, then angle delta stop changing here. But at point P, can observe here, the electrical output is more than the mechanical input. Therefore, there is a deceleration. Because of that, what happens here? The angle delta is goes on decreasing. Because at point P, the electrical output is greater than mechanical input. Therefore, delta is goes on the decreasing. Therefore, the operating point will shift from P towards O. But the speed here is synchronous speed. The speed is goes on decreasing. At O, you are getting the less than synchronous speed. At O, you are getting less than the synchronous speed. But at O, both electrical output and the mechanical input are equal. But because of the inertia, once again, the delta goes on decreasing. Delta goes on decreasing. Then the cycle repeats, so that because of the damping torque, then ultimately it is settling down to new value of O. So that during this, there are two areas we come across. One is, that is the first curve what I shown here is, it is a healthy condition. The curve B, which is meant for the fault on one line and cleared by the opening the faulty line. Here, under fault conditions, circuit breaker opens the line, increases the impedance between the generator and the infinite bus. Therefore, curve B is lower than the curve A. That is quite evident because the reactance is increased. When the fault is cleared, operating point shift from M to N. That is the same thing I explained here. M to N. PS remains the constant. At N, the PS is greater than the P. PS is greater than electrical power output. That is, the rotor accelerate and delta increase. Operating point is shift from O from N. That is, N to O it is shifting here. As it reaches O, accelerating power becomes 0 and the speed is more than the synchronous speed. I told you at N it is synchronous speed. Here there is an acceleration, the speed is more than synchronous speed. Okay, here the area here is equal to this area. That is, MON area is equal to OQP area, so that A1 and A2 are equal. Therefore, the system is stable. The same thing is explained here, that is from O to P. That is, I will show you once again. Here the curves. That is, from From O to P, the rotor experiences deceleration. Because n it is the acceleration, the speed goes on increasing and it is the more than the signal speed at O. When it is moving from O to P, there is a deceleration, but the speed is more than the speed at an infinite bus till it reaches the point P, where the relative speed of the is 0 and the torque angle ceases to increase. That is, when it is reaching point P, the speed becomes synchronous speed and it is stop changing, angle stop changing at point the P. Then we are considering at point P, output is greater than input, that is electrical output is more than the mechanical input, therefore there is a deceleration, therefore speed goes down related to infinite bus. Here afterwards, the speed goes on decreasing, so that at point O you are getting the speed less than the signal speed. The same thing is done here till it reaches point O, where the speed is minimum. The torque angle continue to decrease till it reaches the point N. Once again, it is because of inertia, it is moving towards N, where again the speed is equal to the infinite bus, that is signal speed. The cycle repeats itself if damping is not present. Because of the damping, ultimately it is settling down to the point O. If the damping is not there, it is go on oscillating between P and N. It is found that in practice, because of the damping present, the rotor operates at point O on the curve B and the torque angle delta S. That is, ultimately it is settling that point O with the angle delta S. Then what should be the transient stability limit? That is, here I told you the area this, that is MON, area is equal to OQP area, then A1 is equal to A2. Then if the situation arises here such that, I'll show you here, this is the operating point, the previously, but the input is very large here, so that you can see here the area A1 is just equal to area A2. Area A1 is equal to A2. Suppose if you are making any attempt more than this value, in that case the system is losing its synchronism. This point, that is a P, the corresponding to B, that is what you are calling, it is the point where it is critically stable. It is a critically stable. Here afterwards the system is losing its synchronism. To determine the transient stability limit, for this case we should raise the input line PS such that the area below PS and the curve B and the above the line PS and the curve B at the intersection of PS and B are equal. That is what I am showing here, this A1 and the A2. This is illustrated in figure. The value of PS corresponding to this situation is known as transient stability limit. It is the point B is called as the transient stability limit. If you are increasing your input beyond this, then the system is losing its synchronism. Here A1, area A1 is equal to A2. Then you can observe here, that is, I told you, it is stable when area A1 is equal to A2. You are cleared the fault here. Then area A1 is equal to area A2. This is a stable condition. Then you are clearing the fault such that this area A1 just equal to A2. Then it is a critically stable. You can see here, it is A1 here. It is A1 here, but if you are going beyond this, then A2, here A1 and A2 are not equal. In that case, it is the unstable. This is how to analyze the system for stable, critically stable and the unstable condition. That is, we have taken the condition in the first case is a sustained fault where the faulty line is taken off. But in the second, the application of the equal area criteria, Once again we are considering generator connected to infinite bus, and fault is cleared after some time. There is a fault is occurring on the second line. It is the fault is for some time it is there in the system. After some time the fault is cleared. The fault is cleared so that the system is once again healthy. Now I will draw here the three different power angle curve. One is the healthy condition, that is the curve A is for healthy condition without any fault. When there is a fault is occurring, the power angle curve will drop because of the reactance is increasing. In that case, it is dropped to the power angle curve is dropped to B. Subsequently, the fault is cleared, therefore the power angle curve is increased to the curve C. That is, A is for pre-fault, B is for during a fault, C is for after clearing the fault. Then previously the point is operating at O. When there is a fault occurs, the operating point is O is shifting towards O dash, because when there is a fault occurs. This is meant for the fault. Then the operating point is goes on increasing here, and when it reaches at M dash, the fault is cleared. The fault is clear. Then suddenly the operating point will shift to M. That is, when there is a fault occurs, the operating point is shift to OM dash, O dash. Then because the fault is there in the system for some time, it is the operating point is shift towards M dash. When it is reaches M dash, the fault is cleared, then the operating point is shifting to N. Then because of acceleration and deceleration, then it is reaches N. Then there are two areas will come across, that is area 1, that is acceleration area, and deceleration area. Here A1 and A2 are equal and the system is stable. Ultimately the system is operating at this particular point, that is the point E, when the fault is clear. When the fault is clear. Before that, it is operating between, that is acceleration area and the deceleration area, both are equal, and the system is what we are calling as the stable condition. That is very simple. That is O to O dash. Then if you are not clearing the fault, it is losing its synchronism. But when it comes to point M dash, suddenly the fault is cleared, then the operating point is shifting to the post fault curve, that is to M. Then M onwards, it is because of the inertia it is moving to N, and ultimately it is shifting to the point E. Before oscillation, then there are two areas, that is A1 and A2, they are equal, therefore the system is what we are calling is the stable condition. This is how we have to explain for the application of the equilibrium criteria for fault cleared after some time. Okay. In the next, that is, if you are increasing PS and little bit above this line, that is just I will show you here. If you are operating, if you are changing your P dash to this value, in that case your A2, that is A2 is also changed, and it is reduced. The area A2 is also reduced. Here you can see here the system is now stable. There is one point, the critical point, once again A1 is equal to A2, where the system is what we are calling is the stable condition. This is how you have to explain the application of the equal area criteria for the fault on a system, that is a generator connected to infinite bus.